Okay, so I'm going to start your class a little bit differently than I did the others. I need you to find page 8 in your notes. So that'll be on the back of page 4 since yours are front and back. And we're going to go all the way to the bottom. And I want you to read the very last paragraph that is written there. Just read it. Okay? We all got it? So, everything that we do today, we're not going to stress over. No, we're not. Okay? We're not going to stress over at all. In fact, if you have your AP chemistry equation sheet with you, you will see where it says atomic structure, which is the unit we're doing, there are only 2 equations that they find are important for you to know. And they put them on the sheet, so you don't even have to memorize them. And all of the constants are in the box right next to it. Okay, so as far as math goes, or any like math equation that you would need to know, we're going to do that first in this lesson, and then the rest of it is pretty much the stuff we did last year, where we did the NLMS, you know, where we drew the electron configuration out, and then we would give it energy level, the spin, that kind of stuff. Okay, that's the stuff that you're going to need to stress about. Okay, so everything from here on out for the rest of the year, if you had me last year, is review. You have done this already. My AP biology people, well, you just keep trucking along like it's all new, and you'll be fine. It's not difficult, and I'll teach it just like it's new, so you don't have to worry about that. But I just wanted you to not stress about this, because there's a lot of like quantum physics in it, okay, in this very first section, and it's a lot of history. Like, we know now that light behaves as a wave and a particle. We know that, okay? We didn't always know that. Used to, they thought it just behaved as a wave. And so when it came along that light also behaved as a photon, it was like Satan had just made an announcement, okay? I'm serious. For people back there, like back then, like literally, like they were like nailing people to the doors of the churches, like shun them, do not let them, because they think, you know, like energy has mass. It was a big deal back then, okay? Yeah, I mean it was bad. Like they really thought like Satan had just made an announcement that light could also be a photon of energy. It was like, what? So a lot of this stuff is very like history. A lot of it is very like physics-ish stuff, and you're in chemistry. So it's hard to like tie the two together, and I will be honest with you, I'm not a huge physics person, okay? Like, I loved it in high school, and then I got to college, and that ruined it for me. I hated every minute of it. I took Physics 1 and Physics 2, and I hated every minute of both of them. But if you are a physics person, then I encourage you to learn all you want to of this, enjoy it, soak it up, and then you can come explain it to me, all right? So, go for it. But I just wanted the rest of us who are just going to nod our heads, just nod your head and say, got it. I got it the best I can. I've got it enough where if I had to work this equation, I can do it. Okay? And don't necessarily stress over this theory. Stress over what we do from tomorrow for the rest of the unit. Don't stress over today. Are we good? Have I pep talked you enough that you're not going to freak out on me today? Okay, that's what I want. All right, electromagnetic radiation. Electro sounds like what? Electricity. Magnetic sounds like magnetic, okay? And radiation. So we get that because all electromagnetic radiation has an electric and a magnetic field. So that's why it's called electromagnetic radiation. I know, that was just really complicated, all right? So we can handle this. So what is electromagnetic radiation? Anything that pretty much behaves in waves on a microscopic level, okay? Like, or not even microscopic, because radio signals are not microscopic, but like your UV, your visible light, your infrared, your microwaves, which you use every time you warm up your food. Okay, radio. When you turn on your radio, you tune it to a station, right? Okay, we're getting it to a certain frequency, to a certain wavelength, so we can hear the music that we want to listen to. and then of course X-rays. So we come across electromagnetic radiation in our everyday life. We just don't like pop something in the microwave and be like, hey mom, look, I'm gonna start some electromagnetic radiation. Like, we just don't do it, okay? So, but we have it in everyday life. So since waves are such an important part of understanding electrons and how they behave, we have to know a few terms that go along with waves. And the first one being wavelength. And here's the symbol for a wavelength, and that's lambda. That's what that's called. It's called a lambda. It's a Greek letter. And this is just the length between two crests. Crests happen at the top of the wave. If it's at the bottom, it's called a trough. So it could be crest to crest or trough to trough. Okay, that's your wavelength. So top to top or bottom to bottom, crest to crest, trough to trough. Okay. Then we also need to know what frequency is. And frequency is that kind of like cross between a V and a U. Can't make up his mind. It's called a nu in chemistry, and in physics, they use an F instead of a nu. To me, it makes more sense to use the F because it's frequency, and it just makes more sense, but you could use either. It does not matter. So you can use the nu symbol, or you can use the F for frequency. And this is the number of cycles per second that pass a certain point in space. So, like, let's say that this, from here to here, this all happened in 1 second. Okay, so I would say, okay, so what's the frequency of that? So since I started on top here, I would say, well, this is 1, 2, 3, 4, 5, 6, 7, 8. So this has the frequency of 8 hertz. Okay, and that's how we do frequency. Everybody good? We're good. All right, amplitude is the height of the wave, and we measure the height of the wave from the axis of propagation, okay? That's a fancy word for saying we drew a line through the middle, okay? So here's your axis of propagation. So your amplitude is just your height from the axis of propagation up into the very top of the crest, or you could do it from the axis of propagation to the bottom of the trough. That is your amplitude. And these should look familiar. You remember when you did the sine and the cosine waves and all that? Yes? Okay. We used those. We use these terms. And then, of course, with waves, you have nodes. And those are the point of zero amplitude, so they occur at the axis of propagation. So where the axis crosses through the wave, there's a node. 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 So those are the nodes of the wave. And then, of course, velocity is equal to the speed of the wave. So that gives us the equation that velocity is equal to lambda times nu, or velocity is equal to wavelength times the frequency. Okay? Well, all electromagnetic radiation travels at the speed of light. Okay? So the velocity of all electromagnetic radiation we call c, okay? Because c is the speed of light, and we call it 3 times 10 to the 8th meters per second. Okay? It's a constant. It stays the same. Okay? So all electromagnetic radiation travels at that speed, and it is pretty fast. It's very fast. Okay? So we could also say that c is equal to lambda times nu. Or, if you prefer to write it, lambda times frequency, they are the same. You can use whichever symbol you want to use. It does not change. So, since c is the speed of light, c does not change, right? It's a constant. It's 3 times 10 to the 8th meters per second. That's the speed of light. So that means if my wavelength goes up, what happens to my frequency?
Goes down.
It has to go down, okay? Or if my frequency goes up, then my wavelength goes down. So these are inversely proportional. If one is large, then the other is small, which makes sense if you think about it, okay? The larger wavelength, here, this has a larger wavelength than here. So what happened to my frequency? When my wavelength decreased, my frequency what? Increased, okay? So it makes sense. And then here is our electromagnetic spectrum. So it goes from gamma rays, which are the most dangerous, okay, all the way to radio waves. So these, of course, would be the least dangerous, or at least we hope so.
Yeah.
Being that we ride around in our cars exposed to them all the time. Okay. All right, so why are the gamma rays the most dangerous? Okay, what do we notice about the wavelength of the gamma rays?
It's pretty tiny.
It's very, very small. So that means the frequency is very what?
It's
Very
It's a
large.
lot more energy.
Okay, so that means it has a lot more energy because energy and frequency are directly proportional, which means if my frequency is high, my energy is also what? High. Okay, so this is why gamma rays, okay, can be so harmful. This is also why, notice here we've got our X-rays. And when you go in to take an X-ray, what do they put over you?
And radioactive.
Lead.
They put those lead vests on to keep the X-rays from penetrating your soft tissue. We X-ray bones and things like that, but we try not to let X-rays, especially with females, we don't want it to mess up your reproductive organs.
That's great.
So, and you can see why, because they have a short wavelength, which means they have a high frequency. And the more energy you have, okay, the greater your ability to penetrate those substances. Like lead can stop X-rays, however, gamma rays, lead can't even stop. Okay, so as we increase that frequency, then we increase the energy.
Where are gamma rays found?
It's radioactive materials. Like you have alpha, beta, and gamma radiation, and gamma is the most.
Those are like if you have them
Mhm. All right. And so then we have our visible light spectrum somewhere in the middle. So this is the only part of the electromagnetic radiation spectrum that obviously we can see. Okay, this is the only one we can see. So we've got our violet down here. And then we've got our red down here. Which one's most dangerous?
Violet.
Violet, and then red would be the least. Okay, so of course you've got your Roy G. Biv in here. Fun fact, this eye, indigo, there's actually a petition to take indigo out.
So stupid color.
It's like a purple blue.
It
is a
It
purple
can't
blue.
decide. It needs to get it back together.
So
Or
there is a
color.
petition. So maybe one day your kids will come home and instead of saying Roy G. Biv,
Roger there.
they'll say Roy G. Okay, there'll be no indigo in there. All right, to help them remember. I didn't come up with that on my own. I think I got that from Spencer.
I had a pop off book for my
Spencer, you learned something from
I did.
Spencer?
No, I mean the Roy G.
Oh, I thought maybe you learned something from Spencer. I was
No.
like,
rainbow.
it's cool
I knew about the indigo thing on my own. All right, so exercise 1. The brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers when strontium salts such as strontium nitrate and strontium carbonate are heated. This can be easily demonstrated in the lab by dissolving one of these salts in methanol that contains a little water and igniting the mixture in an evaporating dish. Calculate the frequency of red light with a wavelength of 6.5 times 10 to the second nanometers. Now, what that's talking about is, do you remember last year when we put the salts in the dishes and I lit them on fire and they were all different colors?
The green?
Yeah,
You should
that's
do
what
that
they're
again.
talking about. Okay.
Doesn't
So-
salt from the ocean burn green?
Hmm?
Doesn't salt from the ocean burn green?
I don't think so. Because it's sodium chloride, so it shouldn't.
We should test
Unless it's
this.
got something else in it.
That might be.
We should test this. Like right now. Just skip all this and just burn
I
salt.
see your salt right there.
Yeah,
Burn
just,
salt.
anyone got a lighter?
I don't have any methanol.
Oh, what do you need methanol for?
Because you have to put it in methanol to make it burn.
Just spit on it.
No, that's not fun.
It's not fun. Alright, so let's calculate the frequency. So what equation do we know that relates wavelength and frequency?
C is equal to
Frequency.
upside down Y times frequency.
Okay.
Lambda.
So what are we solving for?
We're solving for
Yeah.
frequency.
Frequency. So frequency is going to be equal to what?
That's gonna be C divided by lambda.
There you go. C divided by lambda. So C is equal to what? 3.0 times 10 to the 8 meters per second divided by what's my wavelength?
650 nanometers.
650 nanometers. Why can't I just write 650 nanometers there and move on?
It's not in meters.
You gotta write 6.5.
There you go, because it's not in meters. I've got to put it in meters since that is in meters. 1 nanometer is equal to how many meters?
10,000. Million. Have a number.
1 times 10 to the negative 9th meters. I don't know.
Are you serious?
Yeah.
We can change that.
It's not like a net for
Okay.
nanometers and 1,000 meters.
So that means all you have to do is just take 650 and multiply it times 10 to the negative 9.
Okay.
Okay,
On here.
It's
so that's all that means.
too much.
It's not too much.
I mean, like they're extra.
And so then if I divide this out in my calculator, I get 4.61 times 10 to the 14th. And for my units, my meters cancel. Notice this S is in the what?
Denominator.
Denominator. So I would write this as S to the negative 1. Because the negative 1 just means it's in the what?
Denominator.
Denominator. Or you can just use the unit first. Whatever floats your boat.
What would be the denominator? 'Cause it's all. Oh, never mind.
So why does it give us 6.5 times 10 to the second?
They just changed it to scientific notation.
That's dumb.
Agreed.
You're just messing with
Agreed.
it. Agreed.
Alright, so that equation was easy. We can handle that, right?
Yeah.
We're good?
Yes.
We're good. Alright, so we're still not worried about anything that's coming. So the nature of matter. At the end of the 19th century, physics were feeling rather smug. I'm just going to read this because I find this very interesting. They thought that all of physics had been explained. Okay? So they literally told students, do not go into the field of physics because there's nothing left to discover. We've explained it all.
What?
Okay? They literally thought that they had explained everything. They said matter is a collection of particles and energy is a collection of waves. Period. Everything is explained. There's nothing left to discover. And thankfully, of course, you always have those stubborn people in life who are like, no, don't think so. All right? And so Max Planck came along, and he is the one that came up with the thought of what we call the quantum numbers, okay, or a quantum of energy. So just think of this as, when we think of quantum, we're just thinking of like a whole packet of energy, okay? And so it's not like a fraction of a packet or a little bit, it's just a whole packet of energy, okay? So he made the assumption that there's a minimum amount of energy that can be gained or lost by an atom, okay? That the atom has the ability to gain energy and it has the ability to lose energy. However much it gains, it can also what? Lose, okay? And so he came up with the equation, change in energy is equal to N, and that N there is just a whole number times this packet of energy, okay? So I've got the packet of energy that the electron has. N is essentially, you're going to learn this when we get to quantum numbers, is the energy level. Okay? So as I increase in energy level, then that means my energy just gets multiplied and multiplied. Okay, that's all that N means. So really what you're looking at is just E is equal to H times frequency. Okay, where H is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. Again, on your sheet, so we're not trying to memorize. Okay, it's there. All right, and keep in mind there's no such thing as transferring electrons in fractions of the quantum. Okay, a quanta is that minimum amount of energy, all right, that has to be gained or lost. There's no such thing as transferring just a fraction of the energy. Okay, we either transfer all of it or none of it. Okay, we don't transfer it in fractions. So his hypothesis applies to everything on the atomic and molecular scale. And we're going to learn as we go on. It also applies to, honestly, us. Like, I know we don't see it. We think we just behave as particles, right? Particles.
Yeah.
Well, we actually do behave in wave-like properties. But the bigger something gets, the less that wavelength affects anything. So exercise 2 says, the blue color in fireworks is often achieved by heating copper-1 chloride to about 1200 degrees Celsius. Then the compound emits blue light having a wavelength of 450 nanometers. What is the increment of energy, so what is the quantum, that is emitted by 4.5 times 10 to the second nanometers of copper chloride? So what am I trying to find here? Energy. So energy is equal to H, which is Planck's constant, so do I have that? Yes. Times the frequency. Do I have the frequency?
Oh, no, you gotta find it.
No. I've got to find the frequency. How can I find the frequency?
C over two.
There you go. C over lambda. I know that the frequency is equal to C over lambda. So that's equal to 3.0 times 10 to the 8 meters per second divided by my wavelength. I'm just going to do 450 times 10 to the negative 9 meters. I put that in my calculator and I get 6.67 times 10 to the 14th seconds to the negative 1. So now that I have the frequency, can I find the energy?
Sure, man.
Just plug it in, right? Planck's constant is 6.626 times 10 to the negative 34 joules times seconds times the frequency, which is 6.67 times 10 to the 14th seconds to the negative 1. So what are these seconds going to do to one another? They're going to cancel. And then I'm just left with what? Joules. So I get 4.41 times 10 to the negative 19 joules. Can you do exercise 1 and 2?
Yeah.
Yes. Then you don't need to stress about pages 3 through 8 that I'm about to go over. Okay? And I'm going to try to make them short and sweet and as painless as possible. Got it? And we're not going to stress over it. We're just going to chill with it. Okay? All right, to sum up the photoelectric effect, and we did this last year in pre-AP chemistry. We talked about this photoelectric effect, okay? And so Einstein, after it was supposed that electromagnetic was quantized, he proposed that it could also be viewed as a stream of particles, and he called those photons. So Einstein was the first one to come along to say, not only does light behave as waves, but it also behaves as photons, and electrons do the same thing. It's like they move as waves, but they also move in photons. And he proved this by the photoelectric effect. So what he did was he took light, and he hit the light on the surface of a metal. And what happened is that electrons were ejected off. Okay? Well, what's the only way that I'm going to be able to eject something, to make it move?
Adding energy.
Huh?
Adding energy to make it jump.
Okay, but let's say I've got, let's say I've got this pen, okay, sitting on my stool in front of me. How can I make it move?
Take it,
Well, you adding some.
punch it.
Put in percent.
Okay, I've got to be able to physically, like, make it move, right? I've got to hit it, I've got to pick it up, I've got to do something, okay? So I can't just sit here and play mind games with it, like I am sending energy to you, you will move.
Hope to see you.
Okay. I can't. All right, so I can't just send mind games to a pen and make it move, right? No. So it's the same thing when with the light hit the surface of the metal and the electrons went off. He said, if light was just a wave, how in the world would it make the electrons eject off? It wouldn't. So that meant that light had to behave as a particle. It hit the electrons and it made the electrons bounce off. He said, so the light has to be a particle, and not only that, But the photon also had to have some type of mass, correct? Okay? If it was a mass of nothing and it hit the electron,
Pass through.
it would just pass through. Nothing would happen. And so he said, so that means a photon has energy. It has mass. So that must mean that energy also has mass. And people's minds were blown, and they said he was of the devil.
Slow down there, Satan.
Okay? That's what they said. Slow down there, Satan. Okay? Like, we're not quite so sure about this. But Einstein said, no, it's true. So what he did was he just proved Planck's equation. He said he's right. Okay? Energy does have velocity, but he took it a step further and said not only does it have velocity, but energy also has mass. And so he proved that with the equation M is equal to Planck's constant divided by wavelength times the speed of light. Okay? You with me still? We're not stressing about this. This is just all a bunch of theory stuff.
M is
Okay.
mass, basically, right?
Yes, M is mass.
So that's the mass of a photon of energy.
Okay. So, does a photon have mass? Yes. How did we prove it? We proved it as recently as 1922 when Arthur Compton performed experiments by colliding X-rays and electrons. And he said there is a collision that does happen. It does change the course of the direction they go, so it can't just be a wave. Okay? It's actually a particle that is there. So, what did we learn from this? We learned that energy is quantized, which just means Okay. we can put a number on it. Okay. It can only occur in quanta, in the h times the frequency, and that light behaves as a wave and a particle. So we call this the dual nature of light.
Light.
There we go. All right, and so then de Broglie just rearranged it. He said, okay, well then if mass can be found by using the quantum of energy and the frequency, then I can take the mass of something and the frequency or the velocity that it's moving, and I can figure out the wavelength that it's moving. So all he did was rearrange the equation, and he said, well, wavelength is equal to Planck's constant divided by the mass times the velocity or the speed that it's moving. And so in exercise 3, it asks us to compare the wavelength of an electron that has a mass of 9.11 times 10 to the negative 31 kilograms, aka an electron's mass is very, very what? Very, very tiny. If it's traveling at this speed compared to a ball that has a mass of 0.10 kilograms, so compared to an electron, the ball is very what? Heavy. And the ball's traveling at 35 meters per second. And so he just plugged everything into this equation, right? Okay. And he got the wavelength of an electron is 7.27 times 10 to the negative 11 meters, whereas the wavelength of a ball is 1.9 times 10 to the negative 34th meters. So what do we notice about the wavelength of the electron compared to the wavelength of the ball?
It's very high.
The wavelength of the electron is a lot bigger, which just proved his point. Everything has wave-like properties, but the bigger they get,
It's small.
the smaller that wavelength becomes, so we don't notice it. Does that make sense? And it doesn't affect us. So we focused on more of the small microscopic particles.
You can't see the smaller wavelengths
Right.
visibly, but they're there.
Right. Okay. So the more massive the object, the smaller its wavelength, so therefore we don't notice it. Like the Mack truck driving down the highway, okay, has, all right, wave-like properties. Do we notice them? Do we even care about them? No, it's a massive object, so it doesn't matter. Okay? But it does prove that all matter, not just light, has both particle and wave properties.
Like when they flipped out about the whole light thing, like
Uh-huh.
how did they not understand like they had candles or whatever. You light a candle with a flame, that
Right.
is energy,
Right?
which emits light. So if light's coming from something that they already know is energy, how could that not understand that that is energy too?
I don't know. People are very resistant to change. Does that make sense? Like, if you thought, like, for instance, when Columbus first said that the earth was round, people were like, you're crazy. Like, I can see, like, this room right now is flat. How in the world can you even think that it could be round? And, like, people thought Columbus was, like, certifiably crazy. They're like, this dude has lost his mind. And it's just because we're trained to always think something. Like, this is what is true. And so we hold on to it. And sometimes, I mean, it's so bad, like, you can prove to someone that it's wrong. It's kind of like, the saying goes, like, don't drink the Kool-Aid, or somebody will be like, oh, yeah, he drank the Kool-Aid. Kind of like that guy that had the cult. And he literally made everyone drink the Kool-Aid and die because he convinced them that, like, that's what they needed to do. Like, this was the way to make it.
Drink Kool-Aid, man.
The human mind can be convinced of some things that it's almost scary.
I was just like, cause it just bothered me. Cause like when you started talking about it, I mean, that's just exactly what I thought. I was like, man, we don't just like use just electricity and wires to make light. Like people use like a flame that we do is
Yeah.
energy and lit something to create lights. How did I not get that? Well, why did you even have to do this for me to realize it?
Really
I don't
saved
know.
Christmas years in Canada for like half of their life.
All right, so then we went on to the atomic line spectra and Niels Bohr and what he discovered. So we're going to do a little bit of background of what I taught you last year. Okay, so remember, every electron has what we call a ground state and an excited state. Okay, so if we drew a picture of an atom, we made it a circle. Okay, in the middle, what's the little positive thing in the middle?
Proton.
The nucleus, thank you. Okay, the nucleus is in the center of the atom, and it's positive. It does have protons, though, Alex, it does. All right?
Say my name.
And then remember that the electrons have energy levels, okay? They don't just all float around wherever they want to float around, okay? They are confined within energy levels. And so the ground state is the energy level that the electron can get in that's closest to the nucleus, okay? So is the ground state the same for every atom? No, all right? Because remember, we can only fit 2 electrons in energy level 1. So that's the ground state for those 2 electrons. But when the 3rd electron comes along, its ground state is going to have to be in the 2nd energy level, right? Okay, so the ground state is just the level that's closest to the nucleus that the electron can get, okay? That's where its energy is the lowest. Why? Because electrons have what charge? Negative. The nucleus is positive. Opposites attract. That's where we want to be. Low energy. I'm negative, you're positive, we're attracted, we don't have to do much work to stay here, okay? But sometimes the electron can get excited. Okay, what does that mean? It will absorb energy. Okay, it will absorb the energy. When an electron absorbs energy, it causes it to jump up into a higher energy level. So it jumps up. Here's some more physics for you. What goes up must come down. Okay, so the electron that jumped up is eventually going to what? Come right back down. That leads us to the emission spectrum. When the electron jumps back down, we actually see that happen. How do we see it? We see it happen in the form of color and light. Okay. So there we go. So we did this last year. And you probably did it with Ms. Barton if you didn't have me last year, where we took the gas tubes, we put them in the cathode ray tubes, and we plugged them up, and we sent the electricity shooting through them. Remember, they would glow, okay? And then we took the prism. Y'all didn't do that? Okay. We took the prism, and you look through the prism, and you get a line spectrum. Okay? So you'll see, like, you see a distinct red. And there's an indigo. See where I'm going with this? Okay. So you see the line spectrum, and that is you actually seeing we sent electricity through the gas, so it caused the electrons to get excited and jump up. Well, what goes up must come down, so we can see the electrons losing their energy in terms of the color of light that they give off. Okay. So, for instance, here, I knew that an electron was falling from energy level 5 to energy level 2 because it gave off blue light.
Does this
Or-
only happen with certain gases?
You know, it can happen with any element that you make a gas.
That you make a gas, so it has to be a gas. And then you
Yeah,
run
it makes it easier to see, yeah.
Okay.
Alright. And then from 4 to 2, it was green, and then from 3 to 2 was red. Okay. You still with me? Yes, you're still with me. Alright. So, you made the assumption, the mother of all assumptions, but it is true. Okay, that the electrons stay in the lowest energy state unless we disturb it. If we disturb it, we can get it to change its energy level. Where n is equal to 1, it has the most negative energy, okay? Because we assign negative values as attractive forces. Is the negative electron attracted to the positive nucleus?
Yes.
Yes. So the ground state has the most negative energy, and when we excite it and we move it up, it becomes less negative or more positive, okay? Because we assign positive as repulsive forces. If I take that negative electron and move it further away from the positive nucleus, is it going to be as attracted? No. Okay, so our energy becomes more negative. So what you need to remember for this is that when we read it, like I'll skip ahead just 1 second, and we said exercise 4 says calculate the energy required to excite the hydrogen atom. So to excite it, is it going to have to absorb energy or release it? Absorb. So I know no matter what I get, I'm going to make it a positive number. Even if I set the problem up and it gives me a negative, I'm just going to take the absolute value and make it positive. Okay? Whereas if it said that it was moving to the ground state, I would make it negative. Does that make sense? Okay? I'm almost done, guys, I promise. And then you don't have to suffer through this anymore. So, they came up with the equation, the energy of an electron is equal to negative 271 times 10 to the negative 18th joules divided by z squared, where z is the nuclear charge, so it's essentially the number of protons, okay, divided by n squared, and n we already know is the energy level, or the distance from the nucleus.
Wait, so z squared is basically the atomic number.
Yes.
C squared Steve Tyler.
So, and this only works for elements with 1 electron. So therefore, it really only works for who?
Hydrogen.
So exercise 4 says calculate the energy required to excite the hydrogen electron from level n equals 1 to level n equals 2. So I would just say energy is equal to negative 2 point, let me get there, 178 times 10 to the negative 18th joules times, so we're going to do final minus initial. Where is it finally going to end up?
2.
N equals 2. So I'm going to do the 1 squared over 2 squared. 1 because hydrogen only has 1 proton. 2 because it was in energy level 2. Minus 1 squared divided by 1 squared because that's energy level 1. Do we see that?
No.
Z squared is the protons. It's both the hydrogen atoms, so they both have 1, so I did 1 squared for both. This is the final, where it ended up. This was where it was initially. Final minus initial, okay? So it ended up in energy level 2, 2 squared, okay? Initially, it was in energy level 1, 1 squared.
How do you know it moved up 1?
Because it said calculate the energy required to excite the hydrogen electron from level n equals 1 to level n equals 2. Sorry, I forgot I didn't read it. Okay. So then when I do that, I find that the change in energy is equal to 1.633 times 10 to the negative 18th joules. And then it asks me to calculate the wavelength. If I have energy, can I find wavelength?
Yeah.
Yes, I can, because I know energy is equal to Planck's constant times the frequency, right? So that's the same thing as Planck's constant times c divided by wavelength. So all I have to do is solve for my wavelength, correct? Correct.
If
profits by it, I guess that's just your salary and then the benefits added on.
Gotcha.
You plan, so.
Yes, sir.
I'm sorry,
No, you're okay.
I'll-
All right. So we would just solve for my wavelength here. So wavelength would be equal to HC divided by E. Because if you're solving for something in the denominator, when you cross multiply, all you do is swap places. Okay. So I would plug in my Planck's constant, my speed of light, and the energy I just found there. And then I would get my wavelength is 1.216 times 10 to the negative 7th meters.
Who's on the test?
It's not.
Alright.
That's why I'm not like going into incredible detail right now. Okay. Exercise 5 works pretty much the same way. And then we move on to the start of quantum numbers. Okay. So let's just go over one more thing that you need to know. Well, the bell's about to ring. And so we will hit this very quickly tomorrow, and then we'll move into what you need to know. All right. Y'all did great today. Thanks for bearing with me. Don't let this freak you out.